All right, welcome back everybody. In this video we're going to continue our lesson on using the mean value theorem in support of section 5.1 of AP Calculus. So we're going to look next at example 3. For the function g of x equals x minus 4 over x minus 3, decide if we can use the mean value theorem for derivatives on the interval from 0 to 5 or the interval from 4 to 6. If so, we're going to find c. If not, we're going to explain why not. Let's start with the first interval, the interval from 0 to 5. And the first thing that I should be checking to see if I can use the mean value theorem is if the function is continuous and differentiable on that interval. So if we look at the interval from 0 to 5, there's a discontinuity in this function when x is equal to 3, because that would make the denominator equal to 0. So on the interval from 0 to 5, we can't use MVT because g of x is discontinuous. At x equals 3. And x equals 3 is in that interval, which is in 0, 5. Okay. But for 4, 6, we have no such problem. Okay, the function is both continuous and differentiable. Both continuous and differentiable on the interval from 4 to 6. And the open interval from 4 to 6, respectively. Differentiable on the open interval, continuous on the closed interval. Okay, so that means the mean value theorem does apply. So we're looking for a value of c that makes g prime of c equal to g of b minus g of a all over b minus a. So I find the values of these, g of 6, I'm going to go ahead and put 6 into this original function. 6 minus 4 is 2, 6 minus 3 is 3. So g of 6 is 2/3. G of 4, I'm going to go ahead and substitute 4 in here, and I get 0 over 1, or just 0. And then I also find the derivative of g of x, so that I can set this equal. So g prime of x is equal to low times the derivative of high minus high times the derivative of low, square the bottom, and away we go. And if we simplify all of that, we end up with just 1 over the quantity x minus 3 quantity squared. So setting up our g prime of c is equal to g of b minus g of a all over b minus a. That gives us 1 over the quantity c minus 3 quantity squared is equal to g of b is 2/3, g of a is 0, b is 6, a is 2. If we do the arithmetic here, we end up with the expression that 1 over the quantity c minus 3 quantity squared is equal to 1/3. I'm going to go ahead and solve this exactly, like I would if this were a non-calculator section. Since 1 over the quantity c minus 3 quantity squared is equal to 1/3, that means that the quantity c minus 3 squared is equal to 3. Taking the square root of both sides, we end up with c minus 3 equals plus or minus root 3. Adding 3 to both sides, we do this, but only one of these is in the interval between 4 and 6. If we subtract a number from 3, it's clearly not in the interval from 4 to 6. So the only value that we have that makes sense here is 3 plus the square root of 3. And if you wanted to punch that up on your calculator, you should get a decimal value of 4.32. Or pardon me, 4.732. All right, example 4. This is adapted from the 2021 Calc AB exam free response number 4. I used their graph, but did not quite use their problem. Let f be a continuous function defined on the closed interval from -4 to 6. The graph of f consisting of 4 line segments is shown below. Find the average rate of change of f on the interval from -4 to 2. So average rate of change, again, is the slope between those 2 points. So we're going to find f of 2 minus f of -4 all over 2 minus -4. F of 2, we can read off the graph. It's right there. It's -4. And f of -4 is 0. All of that over, looks like 2 plus 4 is 6. And calculating, we get negative 2/3. Are we guaranteed a value of c somewhere in this interval where the slope is negative 2/3? And you could draw all the lines on here, all the possible lines that have a slope of negative 2/3, and you would see that there's not a single segment where the derivative is equal to that. And of course, this is because we have all these corners, and so the function f here is non-differentiable. And so, does the mean value theorem guarantee a value? No, the mean value theorem does not guarantee a value. C in the interval from -4 to 2, for which f prime of c equals negative 2/3, because f is not differentiable. Not differentiable on -4, 2. All right, let's go over to the next page here. Now that we know the mean value theorem, the intermediate value theorem is another theorem that we learned that comes up very frequently. And I say in this section here, I'd expect you to see use one of these most probably on a free response section in a typical year. Now there might be some years where you don't see it, but I typically would expect you to use at least one of the intermediate value theorem or the mean value theorem on the free response section of your AP exam. It's important for us to recognize the difference between the two and what we can conclude from both of them. Okay, so the mean value theorem, which we learned today, the derivative of a function at a point somewhere in the closed interval must equal the average rate of change of the function. So the mean value theorem talks about the value of the derivative or instantaneous rate of change of the function, and sets it equal to an average rate of change. The intermediate value theorem deals with the function value and function value existence, and so you'll have the y value at each of the endpoints, and every y value in between there has to exist somewhere in that interval. And here in example 5, we're going to go ahead and we're going to use both the intermediate value theorem and the mean value theorem because of the way these questions are asked. So let's go ahead and look at example 5. Mike is flying his drone in the field behind his house. The twice differentiable function h models the drone's height measured in feet at time t measured in minutes. The table below gives values of h of t of the drone at selected times for t. And part A asks us here, for the interval from 5 to 10, must there be a time t where the balloon is 55 feet in the air? Okay, so we know that h of t, we're told, is twice differentiable. That means that it's differentiable. So since h of t is differentiable, it's also continuous. It is also continuous. So we can use either the mean value theorem or the intermediate value theorem on this problem. In this case, we're trying to find, is there a time when the height is 55 feet in the air? So we're talking about the function value, not the derivative. And so, since we're talking about the function value, we're interested in using the intermediate value theorem instead of the mean value theorem. Remember, the mean value theorem talks about values for the derivative or instantaneous rate of change. The intermediate value theorem talks about values of the function. So we've got this function. So since we're talking about function values, therefore, by the intermediate value theorem, h of t takes on all values between h of 5, which is 35, that's the one endpoint of the interval, and h of 10, which is 65. Since h of 5, which is 35, is less than 55, which is less than 65. In other words, we're just saying that 55 is in between those two endpoint function values. That means h of c must equal 55 feet for at least one time value. One time value in the interval from 5 to 10 by the intermediate value theorem. Okay, there's my explanation of my answer to that. All right, part B. For time 10 to 20, must there be a time t when the balloon's velocity is 3.5 feet per minute? Justify your answer. Okay, so now this time we're talking about the velocity, which is the instantaneous rate of change of the height. So we're geared towards using the mean value theorem in this part of the problem. So since h of t is differentiable, that tells us that h of t is continuous on the time interval from 10 to 20 and differentiable on the open interval from 10 to 20. Therefore, by the mean value theorem, there is at least one value of c for which f prime of c is equal to f of b minus f of a all over b minus a. All right, so f of 20 minus f of 10 all over 20 minus 10 is equal to 100 minus 65. Pull those from the table. And over 20 minus 10, that's 35 over 10, or 3.5. So, by the mean value theorem, there is a time t in the interval from 10 to 20 where f prime of c equals 3.5, guaranteeing a velocity of 3.5 feet per minute, since those are my units. All right, and there's a little bit of contrast and similarity between our use of the intermediate value theorem and the mean value theorem, and some possible problems like we might see on our AP exam. All right, folks, that's the end of our lesson on using the mean value theorem. See you next time for section 5.2. Have a great rest of your day.